Howdy everyone, I'm Michael Perch. I'm an associate professor at the University of Texas at Austin, and I record all my lectures to support working professionals, people interested in STEM, and of course my students with evergreen content that outlasts even the semester. Many of my students have commented on the fact that they would like a little more help with the very basics of data analytics in Python, and so I've decided to kick off a series of nice interactive lectures in which I covered the very basics. Today, chapter 1 will be Pandas DataFrames for working with tabular data in Python. Next, we'll do numpy for gridded data and so forth and so on, plotting and a little bit of basic machine learning and so forth. I'm convinced that I can cover, in I hope, a short period of time, the very basics you need to get many of the workflows, many of the projects that you need to construct done. That's my goal today. All right, so this is a tutorial or demonstration of tabular data structures in Python. Specifically, how do we work with them? How do we manipulate them? How do we use them in the building blocks of our workflows in data analytics and machine learning? In Python, the common tool for dealing with tabular data structures is the data frame object available within Pandas, a Python package. It's a great tool. It works very well. It's very efficient. I use it all the time. We're going to cover the very basics we need to work with these data frames or tabular data structures so that we can build workflows around data checking and cleaning, data mining, inferential data analysis, data analytics, and all the way up to predictive models such as geostatistics and machine learning. I believe that if you want to work in Python and build data analytics and machine learning and geostatistical workflows, you really need to be able to work with data frames as it is right now. Let's go ahead and cover the very basics, the basic concepts you'd need to be able to get the job done. Let's review what a tabular data structure is. When we talk about tabular data, what we're talking about is literally a table of data. And many people who've taken a fundamental statistics course will be familiar with this, where the rows are the individual samples, 1 through n samples, and the columns are the individual features that you measure, and they could be a set of predictor features, maybe a response feature or two, or maybe you're working inferentially and there's no inputs and outputs, you're just trying to look at data and understand. Pandas is extremely convenient. The data frame object is optimized, that has a lot of built-in functionality so that you can work with this data structure very well. That's where we're going to make good use of it. Now, once again, when we deal with gridded data, which is very common in spatial subsurface data sets, think of maps, think of models, we're going to deal with ND arrays, and that's in the next chapter. You can go ahead and check out that video. It'll be linked at the very end. All right, so the project goal, let's learn the basics for working with tabular data structures in Python with Pandas DataFrames. Let's go ahead and get started and load the basic libraries. Now, my goal is never to load or import libraries I don't need to use. It just causes clutter and confusion. And if I think about it, the very bare essentials I'll need for this project, this demonstration, will be OS. Now, you'll see why I do that, but it allows us to work with the operating system, numpy as np. Now you might think that's a little contradictory because I told you we're going to do numpy nd arrays for gridded data later, but at times we're going to use numpy functionality and demonstrate the ability to go back and forth. Pandas as pd, as everybody does for the data frames themselves, and matplotlib, the pyplot module as plt, so that we're able to do some plotting. And then I'll show you it's really only being used so that we can add some axes and pretty up a plot that I'm going to show, a couple plots that I'll show. Not a big deal. We'll go ahead and we can just run, and we've just imported our packages. We're doing everything live here today. And so you can see immediately. Now, if you don't believe me that this is all live, well, I can make an error, and you can see right there that, of course, there's no package known as that. We can't load that. Let me go ahead and run it again. So you can see this is all being done live with this code. I want to shout out to Rise for the great package that allows me to be able to do this. I really do like it. All right, if you get an error, if you're missing one of these packages, just go ahead and you can go into a terminal window and do a pip install to be able to load up the package. And you could use other methodologies like conda, of course. I'm old school. I like to set the working directory. I see a lot of people don't do this. The reason I do that is I often work with pretty complicated workflows where I have to load data from different locations. I have to save data. I like to explicitly know where things are coming from and where they're going. So I do like to set the working directory. Go ahead. You can set this to someplace on your hard drive. The data file we're going to work with, you'll see, is available on my GitHub account. So you can follow along, no problem at all. Okay, so we ran that. We've set the working directory. You could, of course, try, messing that up and just see what would happen. And of course, you'll see immediately that if you don't have that directory on your C drive, or if you're going to the cloud or wherever you're getting it from, that you're going to get an error. You get the error trace is pretty simple here, just telling you that that location is not available. Let's go ahead and just run that again, clean that up. Loading data. There's a variety of ways we can load data. The multivariate spatial data set that I want to work with is right here. If you click on it, you'll find that it'll take you to my GitHub account. I do share a lot of synthetic data sets, as you can see right here, for all of my well-documented workflows that I like to share with my students. So that is available. You can just click on the link and get there. Download it locally. You could even put its address right there. Not a big deal. Go ahead and we can load that data. And when we do that, I always like to include a head command. It's not a bad idea. You can immediately refresh your memory on exactly what it was. Head command, of course, just gives you the first specified number of records. And you could, look at any number of records you want to look at. And of course, there's tail command and so forth. Other ways to preview. I do think it's pretty instructive to also consider the opportunity to just slice the data and print. If you look carefully at this, the DF, we've loaded up the data frame as DF. That's now our data frame. We've loaded it up from the data file. And so we can start using built-in functionality like ilock, which I'll explain shortly, is an ability to slice it. And what it's doing right here is taking the 0 through 4th sample and all of the features. And if you look at that 0 through 4th and all the features, now you see there's a little bit of a wrap here. It's not as nicely formatted as the head command when you print it like that, but at any time you can do that. Also, if you're ever working with one of these functions, built-in functions, you want to just recall what's available. Hold down Shift and Tab, and immediately you'll get the doc string. So you can look and see the only argument that we're able to put in here is n, and it defaults as an integer of 5. And if you click right here, you can look through and see n is the number of rows to select or to display in the command. So we can get rid of that. At any point, you can check and see what's available as far as the functionality. Default was 5. And so if you go ahead and run it, you'll see 0 through 4. You got 5 records. I know Python in general indexes from 0 to n-1, and so you just got to get used to that. Even these columns right here, this is 0, 1, 2, 3. So if we ever try to use an integer to refer to, or index to refer to the columns, this is 0, this is 1, this is, you see. So it's just something to get used to. Some programming languages do index 1 through n, but Python does not, and that's fine. All right, so there's many different ways we load. I know I've kind of missed out here. I could have shown methods to load directly from Excel. You can check out the docs for Pandas and you'll see there's great functionality to be able to just read Excel. You can specify the sheet. You can specify exactly what range or what cells you want to try to copy across. It's very straightforward to load from Excel. So you can use other types of formats, of course. Whenever I load data up, it's always a good idea to review the statistics. This is all part of data check, data QC and QA, quality control and quality assurance. And you'll want to take a look and just see if there's anything unusual going on. You'll notice this describe command is built directly into the data frames. It's a member function. And so as a result here, it's going to give us a nice summary table. You can in fact control the specific percentiles that are viewed, and you can change other parameters. How do you find out? Do Shift Tab. You do Shift Tab and you can see immediately that there's all kinds of functionality we can build on. Percentile, a list like of numbers, optional. So I think that's really fun. I do work in a world where we often do use not the quartiles, but the P10, P90. That's pretty common. So you can go ahead and just do percentiles. Now it said it needs a list, so let's make a list. 0.1, 0.9. And if we do that, we rerun that command. You can see now we have the 10th percentile and the 90th percentile instead of the P25, the lower quartile and the upper quartile, the P75. So really, really cool. We can do a lot of great things. Another really instructive thing to do is to realize that Python allows you to chain commands up. The output from this command is in fact, well, what is it? Let's go ahead and just type. I love this command. I do this constantly to debug and understand what I'm doing when I'm learning new things. But we can go ahead and check and see, what did we make? Well, it's a data frame. Isn't that cool? So the output from this command is a data frame with the statistics. So let's go ahead and rerun it and get our data frame back. Just visualize it. And we can realize that we can actually transpose a data frame. So I can go ahead and do a transpose on this. And some of you might find it more convenient. I find this easier on my eyes, in fact. In this case, where I have a few features, to just look at them like this, with the features on the rows and the columns, the statistics, the summary statistics. So we can go ahead and check that out. Just a couple of ideas. I'm not going to go into data QC. Like, of course, I'm going to be looking for extreme, minimum, and maximum values. I'll be looking at skew. I'll be looking at the count to see if I have full count. Do I missing values? Well, no, it looks like I have 200 samples consistently. I'm not missing any sample values anywhere. I don't have an imputation problem. You can see there's so much we can do by just looking at summary statistics. If you looked at my data frame, my naming is not great. I was clearly kind of in the middle of some workflows. I did some stuff. It might not be very useful. It might be kind of awkward to use those names in a lot of my plots. I like to rename features when I can. The way we're going to do that is we're going to use the built-in member function of data frames rename. And you just have to say columns equal, and then you give it the features that you want to change their names. The way this is going to be input is as a dictionary. Dictionaries are super easy to make in Python, but they're really, really great readable code. They're simple to understand. This is the way it goes. Feature names is a dictionary. How do we know it's a dictionary? Well, look at the brackets. Those curly brackets mean a dictionary. And then the format is the first name of an entry, and then the thing you want to store there, the second name of an entry, then what you want stored there. It's totally free form. You can put whatever you want, build your own common dictionary. And now, every time it sees this, it's going to look for that in the data frame, and it'll change its name to that. This, change its name to that. This, you see that? So I've made a nice, truncated, simple naming convention. Instead of all that nonsense about thresholding of 0.3, I've got facies, porosity, perm, AI. They're all consistently named, easy to work with. Okay, so we can rename our features. This will happen all of the time. Pretty common. Slicing data frames. Now, I already showed you a slicing of a data frame using the iloc command or built-in function for the case of trying to just do a quick preview. It wasn't nicely as formatted as the head command, but let's go ahead and do this. What we're going to do now is we'll use iloc, which is a methodology that will expect indexes, integers for the rows and columns. The first part's going to be the rows, the samples. The second part's going to be the columns. So the way I would read this is take this data frame, slice from the 0 to the 4th. I know it's a little confusing, but it's not actually the 5th record, it's up to the 5th record. So in other words, the 4th record. Now, the way I like to think about it is 0 through 5 is going to give me 5 records. 0 through 5 minus 1, 4. Okay, so I'll get the first 5 samples by doing that, and then the features I'm going to get, well, 0 and 1 are removed. And if you think about it, 0 and 1, as you saw previously, was my x and y. So all I'm doing is removing the x and y. I'm doing something multivariate. It's not spatial. I don't need that. And so let's go ahead and we'll just run that. And look at what happens, 0 through 4. And we remove the x and y. We have created a brand new data frame that is a reduced version or sliced version of the original data frame. Why would you do this? I find that if I'm building a workflow and I know I'm not going to use X and Y, right at the beginning I just remove it. That simplifies the data frames I'm working with. What I find is that if I can strip down and use only the features I know I'm going to use in the workflow, if I can only have those available, there's less likely you'll make a blunder. Now, I don't know about you, but I've worked in many cases where I've got hundreds of features, and by doing this, it's saved my sanity because I can visualize and look at the data more quickly. It becomes much more efficient. So I recommend using this type of methodology as part of your cleaning and preparation. There's another methodology you can use, and it's the lock command. If you look, the other one's just iLock using indexes, and this is just lock. What's interesting about it and what I like about lock, it's very much the same. We're going to do lock, and then this part right here is saying take the first 4 samples. But now if you look, instead of using indices for the features, I'm able to use the names of the features. Why do I like that? Readable code. I got to tell you, I look at this, if I was to actually do it by the names, this would be like 0 and I don't know, what is that, like 3. I'd get mixed up. I wouldn't be able to read the code if it was indexes and I'm trying to take various different features and mix them together. So I do like using lock for good code readability. Let's go ahead and just run that. And you can see it's super easy to do. So I find this is much better for code readability. It's very straightforward to be able to look at this and realize that, well, we can just go ahead and at any moment we can just add in a new feature in this list and we rerun the code. And look, we just added Y. So very straightforward. I use lock probably more often than iLock because from the context or from the perspective of easy code readability, because we can use the names of the features or the columns rather than their indexes. But other than that, not a big deal. We've been talking about making copies of things. Let's define something very important in coding. And it's kind of an advanced concept, but it will eventually impact you. I've had times where I mixed this up and then my debugging was a nightmare. I just couldn't figure out what was going on. My complicated workflow started to do some weird things. We need to know the difference between deep and shallow copies. The way it works is this. It's really straightforward. A shallow copy, when you say copy this thing, this object, to something else, a new object, a shallow copy is going to actually make a new pointer to the same memory location. If you change either one of those, it will change both. In other words, you haven't really made a copy, you've just made another pointer or label to that thing in memory. A deep copy, you actually take that thing in memory, assign more memory, make a brand new copy, and if you change either one, the original or the copy, it only changes one. Now that's where you'll get really confused because you might have a shallow copy when you thought it was a deep copy. You do manipulation and then your original object got updated. It changed. So you can see how that can really confuse us. Now if you want to do this, to do the shallow or deep copy of things, one of the best way to do is just explicitly. That way you just know which one you have. And you can do that by doing, first of all, making a copy of the data frame, a built-in member function called copy. It has a argument which is called deep, and it defaults to be a deep copy. Now that's good to know. There's many operators within Python that default to be shallow, so there's no clear convention. But if we set it as deep equals true, which I like to do, even though it's a default, I like to be explicit when I code so I don't get confused. I make a deep copy of the data frame. df, deep copy, is a brand new deep copy. It's a new object. Now I go to the 4th sample, well, which actually the 5th is 0 through 4. Acoustic impedance, I'm going to change the value to 0.4 to 4.0, and then I'm going to go ahead and take a look and preview it. Did I make a deep copy? Okay, acoustic impedance is 0, 1, 2, 3, 4, and the value is not equal to 4. I made a change to the copy, and it was not reflected in the original data frame. So I can see right there that's a deep copy. They're not sharing the same memory locations. Okay, so that's a good way to do it. I should note that we already showed you how to do lock, iLock. They default as deep copies. So when you're making those slices, you can check that. They're in fact deep copies, and so if you make changes, it's not going to go back and affect the original. Now let's show you a shallow copy example. Well, this is the world's simplest thing to do. We just rerun the code, but set deep as equal to false. Now we've made a df shallow copy. This is our shallow copy of the original data frame. We're going to do the same thing we did before. We're going to change the third sample, well, the fourth sample, 0 through 3, acoustic impedance to 0.4, and we're going to go ahead and preview that. If you look really careful, acoustic impedance, 0, 1, 2, 3, 4. You see what we did? We are looking at the original data frame. We made the change on the copy and it's reflected over there. That's shallow copy right there. If you think, well, really? Did that just happen? Well, take a look at this. See, sample number 4 from the original data frame was 3.979. Let's go ahead and rerun this code. Look at that, just updated to 4. I'm making changes on the shallow copy and it's changing the original object. So let's be careful about shallow and deep copies when we do anything in Python, and specifically when we work with our data frames. Okay, how do we add a new feature? Super easy to do. We can add a brand new column to our data frame. The way it works is we're going to add it as a one-dimensional array. It has to be in the same sample order. So in other words, its first element must be the value for that feature for the first sample, the second to the second, the third through n. It has to be in the same order, has to have the same length. You can't take a one-dimensional array of 100 samples and add it to a data frame of 50. Now there's advanced methods to do that, but we're not covering any of that. We're assuming that we have equal samples for all of the features, and that's expected with our data frames here. So let's go ahead. We'll use numpy here. I told you we're going to make use of numpy. Numpy has a built-in function, zeros. We'll take the length of the data frame. I'll explain that later, but that's just returning the number of samples. So we're saying make me an array of zeros of the number of zeros will be equal to the length of the data frame. That's called zeros. And then we'll say the data frame zeros, this is the name of the feature. Right here, that's the new feature name, is equal to that array. They don't have to be the same names. In fact, let me just go ahead, just in case anybody is confused by this, I'll go ahead and just change the names. You can see this is an array of zeros, and that's just the name, a string. Now let's go ahead and run that code, and you notice we have a new column now, a new feature called zeros. Okay, super easy to do. We can do this at any time. We can add new features, and we'll do this. We'll get more complicated with it. Now that we've added a column called zeros, let's learn how to drop that column, because as we go along in our work processes, we're probably going to be adding new features, and they might be intermediate features. They might be part of a calculation, but we don't want to keep them at the very end. We can use the built-in member function for data frames called drop. If we specify the axis equal to 1, it's going to expect to receive the name of the feature that you want to drop. Axis equal 1 means drop a column. So if you run this command, you remember what we had before. We had that zeros, and now we've copied over it. So df is equal to df, now drop zeros. You have to do this. When you do the drop command, its output will just be the data frame. You have to reassign it over top of itself. Make sure you do that, otherwise it doesn't happen. And so now when we preview df head, you can see zeros are gone. So we did that. That worked. We actually got the job done. We removed a feature from our data frame. Very useful step. You might wonder, we removed a feature, a column. Can you remove a sample? And of course you can. The way you do that is you use the same member function, drop, and you specify axis equals 0. That means you're going to remove a row, and all you have to do is give the index of the row that you want to remove. This is really cool. We can actually see this quite clearly. If I run this command, 0, 1, 2, 3, whoa, 3 is gone. It's now 4, and so clearly we have, you can go back and look at the previous data frame, and you'll see we have now dropped a sample from our data set. I know dropping data can be very dangerous. You got to be very judicious and careful about this, but I still think it's very good to show how to explicitly drop a sample. To do that, you may need to do that as part of your workflow. Let's talk a little bit about feature engineering. There's so much. I have lectures on YouTube where I spend a lot of time in feature engineering, dimensionality reduction, and so forth. But let's go ahead and just talk about a very simple approach to feature engineering. This is the idea when I want to apply mathematical operators to existing features. For example, if you're working with porosity, which can be represented as a percentage or a fraction, avoid space over the total volume of the sample or the rock, we might want to move back and forth. So here's an example right here. If you look carefully, you'll realize that our original porosity was in fractions, but we may want it as a percentage. And so what we can do is we can simply do this. We can say df porosity 100, in other words, based on 100 out of 100%. This is the name of the new feature, is going to be equal to the previous feature, porosity times 100. Now the way this math gets done is it's going to very efficiently go sample by sample, apply that scalar to porosity, and then assign it to the new feature. So we'll look at the output and you'll see it's going to map directly across. It's sample by sample, and it's actually mathematically or code-wise very quick. Another calculation, this is more like expert-based feature engineering, but maybe you want to create a new feature that's a ratio of permeability, the ability of fluid to flow through the rock, divided by porosity. Now, this can be related to what some would call a rock quality index. Often you'll use a ratio like this, some formulation. Or if we're trying to do a calculation like Lorenz coefficient, we need to do this calculation. Also used often for heterogeneity measures. Okay, so we can go ahead and we'll take the feature permeability divided by porosity. It's going to go sample by sample, and after every division assign it to the new feature, and so it's going to match up perfectly. And let's go ahead and confirm that to ourselves. If you look right here, the original porosity 0.1184, and the porosity is a percentage, porosity 100 is 11.84. So it worked. It's very straightforward. If you look at perm-pore, if you take the permeability of 6.1, so forth, and you divide by 0.1184, that's how we get 52.1, and just sample by sample it did that math. So this is very straightforward. We can do some very simple feature engineering, make new features to work with. It's great, very powerful. You might also want to do some type of conditional manipulation of the samples when you create a new feature, and a perfect example of that is you want to build some type of new categorical feature based on a thresholding of a continuous feature like porosity. Well, to do that, what we're going to go ahead and do, you use the numpy command where. Now, what is actually going to happen here is that the where command will accept a Boolean array as the first input, and that Boolean array, every time it is true, it's going to go ahead and it will assign high, the first value right here. So this is the true case, and then this is the false case right here. So it's going to resolve this Boolean operator, check for true or false. Every time it gets a true, it's going to say high every time. So in other words, porosity greater than or equal to 12% or 0.12 fraction. And it'll say high. Every time less than that, it'll say low. And the output will be a categorical string array. Now what we can do is that array right here that comes out of this command can be passed into a new feature called T-porosity, which for me meant truncated porosity. In other words, just broken up into two categories, high and low porosity. Now let's go ahead and just see if that worked. If you look really carefully right here, porosity less than 12% low, porosity greater than 12% high, and so forth. So that worked. We did a truncation for building a brand new categorical feature. This is very useful if we're trying to do, I often do conditional statistics. I like to break things up and look at the different distributions, violin plots, and so forth. You can easily use this methodology, this approach to get that done. Conditional manipulation. You can do much more complicated conditional manipulation. And here's an example right here where we're in fact doing the conditional manipulation and we're integrating more than one feature within this equation. And so we want to assign a permeability cutoff. The way we're going to do it is we're going to look through the samples, and if porosity is greater than 12% or greater than or equal to 12%, we're going to say keep the permeability value as is. If less than that, we're going to say, you know what, truncate or assign a very low porosity value. In other words, we're saying at that low permeability, we don't effectively have flow. That pore volume is not contributing to any type of flow behavior in the subsurface, be it a water aquifer, be it oil and gas, be it geothermal. It's all the same. It's just not going to flow, and then we'll assign porosity very low, and that'll remove the volumetric. For that location, we're going to say, well, there's no flow contributing. We're not going to have any volume contributing to the flow, be it water, whatever it is. So here's an example where we use multiple features in our conditional statement. Very powerful, simple, easy to use. How about finding missing data? Well, in our data set, I've already told you we don't have missing data. We looked at the data frame describe command, and it was 200 samples every time. We can look at the data frame, and we can look at it, and we'll do this right away. We can look at the length, number of samples. We'll see it's 200. What we'll do then is let's go ahead and use the lock command where we can access a single sample. This is going to be sample number 1. Remember, that'll be the second sample because there's 0, 1, and so forth. And porosity feature, and let's set it to not a number, a nan. Now, that's another reason I use numpy, because numpy has that built in as a label. So we'll go ahead and say numpy.nan. We're going to print that. We're going to go ahead and say number of null values in our data frame. We have a built-in function is null. And what is null is going to do is going to give us a two-dimensional Boolean array, and we can sum twice. We'll sum over the rows. We'll sum over all of the sum of the rows, which will be a one-dimensional array. And the result is we're just summing all of the true values. And so we are effectively counting the number of nan values. Then what we can do is we can take that same command, we can specify and say we're just looking at the porosity values because we know we put the nan value in porosity. And the result here is we're going to create a Boolean array, and that Boolean array will have true every time we have a nan value in porosity. And then we'll go ahead and we'll extract those rows into nan rows. And nan rows is going to show us the samples with the nan values, and then we'll just print that. So let's go ahead and run that and see what happened. The first thing we're going to notice, number of null values in our data frame, it correctly identified that we had 1. We had add 1 right here, and when it checked, it did the double sum of the two-dimensional Boolean array. It found that there was 1 value. Then when we applied this command and we said, well, give us the sample for which, the sample or samples for which porosity has a null value, it in fact gave us sample number 1. Here's the index, here's all the values, and porosity is a nan value right there. So guess what? It works. This is a very simple way to be able to find nan values and look at those specific samples. We could also use conditional assignments, as we just showed previously, to assign a label of missing samples with missing values. Then when we plot, we can look at and illustrate or highlight those values. I like to do that specifically if I'm going to do imputation. That way I can check the locations I imputed at, and I can make sure they make sense. It's always a good idea. If you're curious about that, I do have a workflow on my GitHub account where I do imputation and explain that type of workflow. Now I'm talking about imputation, let me just mention likewise deletion. If you're not sure what that is, it's kind of the worst way to do imputation. It's usually not a good idea. But what you do is you look for any sample for which you are missing any of the features and you remove it. That's likewise deletion. So we can use a built-in function, the member function, drop na, in the data frames to be able to remove all samples with nan, not a number, entries from the entire data frame. To do that, we'll go ahead and we'll use df drop na. We get to specify right here how we're going to decide to drop or not. And this is pretty cool. You can go ahead, if you look at how, we can do any or all. The default is any. In other words, and I like to put it down, I like to put the argument any, even though it would have defaulted to any, just so it's readable code. But what you can see right here is that if any of the features are missing, it drops the entire sample. Okay, now you could do all, where all features must be missing for you to drop. You can make a choice on those. Likewise, deletion is the case of you drop if any are missing. Let's go ahead. Are we going to see that drop? Now, if you look, sample 0, 2, you remember we added porosity as a nan for sample number 1, and now when we created this new copy of the data frame over top of itself with any rows with nans removed or missing values removed, sample 1 is missing now. So we've just done likewise deletion Use it cautiously, probably not the best idea. Better to get into imputation, feature imputation. We've now done it using just built-in functionality with DataFrames, which I think that is a nice way to learn more about it. Let's talk about conditional slicing. Let's get more complicated in how we're removing or slicing samples. And I think this is really cool. What you can do is you can go back to the lock command, and then the lock command, you can just specify the specific condition. If you want to do multiple conditions, you can just use the AND operator, and you're saying I need this condition to hold, this condition to hold. What this is doing is it's going to go ahead and look across your data frame. It's going to look for all cases for which porosity is greater than 12%, permeability is greater than 10 millidarcies, and the result is going to be a one-dimensional array that's Boolean. When you feed that in to the lock command, it's going to say just give me those samples. So df extract, I could have called this df good porosity and good permeability. It's going to give me just those good samples. And so let's go ahead and run that code. And if you look really carefully, you're going to see 2, 6, 7, 13, 15. df extract with only the good values has now lost a lot of the samples. And if you look really carefully at it, you'll see that the porosity values are always above 12. The permeability values are always above 10 millidarcies, and so it's worked. You could check all of them. You could check the statistics and you'd find that's the case. Okay, so we can do all kinds of conditional slicing. We've shown you how to do truncations and assigning categorical features. There's a lot you can do with that as part of your data preparation for building a machine, doing geostatistics. Let's kind of back up and say, how would you make a new data frame from scratch? Because what I've shown you was I just loaded the data frame from a comma delimited file, and I told you we could load it from Excel, but let me show you how you build one from scratch. One way to do it is you can say make a new data frame from a set of one-dimensional arrays, and the one-dimensional arrays will store each one of the features. They must have the same size, the same sorting, and that makes sense. They can't be scrambled. The first element in the first array must be the same sample as the first element in the second array, and so forth. What we'll do here is we can extract, because I didn't have any arrays sitting around, let me just show you taking our current data frame. We'll take porosity. Now when we do this, this is going to give us a series, which is an individual column within a data frame. It includes the name. But to prove it, I want to go ahead and take and do a dot values. That dot values will turn the series into a one-dimensional ND array from numpy. And so this por is a one-dimensional array with all our porosity values. We'll do the same thing for permeability. Now look at what we do. All we have to do is do pandas, PD, data frame, and we include a dictionary. The dictionary is the name of the feature, and then the one-dimensional array-like object with those values, and the name of the feature, and the values, and so forth. And if you run this command and you take a look at what we just created, df_new is a new data frame. So it worked. We can actually make a data frame from scratch. All we have to have is each of the features in one-dimensional arrays with the correct sorting and length and size. So they got to match up with each other, of course. Okay, so that's how you make a data frame from scratch. Let's just cover a couple things about basic plotting. I generally use Matplotlib, Seaborn, other packages for my plotting, but Pandas does have some built-in plotting functions, and I think it's a good idea to mention them. How do we do line plots? Now this is a very simple thing to do. There's various types to choose from. We can do various types of plots. I'll demonstrate a line plot, but you could try on your own. How would you do it? Well, I can go df, the name of the feature. This is going to return the series. And then I do dot plot, and I just say kind line. Now you could put bar, box, or whatever other kind, and you can specify other parameters like the color of the line and so forth. Notice here, this is compatible with Matplotlib. I can go ahead and just put in the names of my labels on the X and Y axis, the title and so forth, and so I can clean up and get a nicer plot. If I do that, it's not bad. You'll note the line plot is simply just going across and just showing you the values of porosity along the data frame from samples 0 through 199 n minus 1 right there. I'll show you what it looks like if we go ahead and just get rid of that and we just look at the default plot. In other words, all I did was say hey pandas, make me a line plot, this is what it looks like. So people who are students in my class know that I insist on axes labeled, captions, titles, and so forth. And so I think that's important to show that. Okay, so that's a line plot. I like making histograms just as much as anybody else working in data analytics. How can I do it? Well, I'll use the exact same command and I'll just say kind equal hist. You'll notice that if you're used to matplotlib and you use the other arguments like the color of the bars and the edge colors and so forth to make it kind of cleaned up and look nice, it has the same arguments right there. And you go ahead and run this. And look, I get a nice looking histogram. You can do plotting directly in Pandas using your data frame. So the built-in functionality around plotting, I'm not going to go into much more than that. You might be a person who wants to kind of access the actual member objects inside of the data frame. You want to actually get at the, I guess I could say, the nuts and bolts, the guts of the data frame. You can do that at any time. In fact, you can access index will give you information about the sample index, so all of the indices that are included in the current data frame. Columns is a list with all the names of the features. Values is in fact a two-dimensional array with all of the actual values from your data frame. And so I can go ahead and run this command. I'm just printing each one of those, and you can see 0, 2, 4, 5. We had removed in the original data frame sample 1 because we'd assigned a nan value and we did a drop na. You remember that? So we've actually, you can see these are the actual indices all the way up to the end, 199. You can see the names of all the features. You can access that at any time. You might have some type of code where you want to actually access all of those feature names so you can automate plotting or something. And then if you look carefully here, you'll see the actual values from the data frame. Now you'll notice ... is to save our eyes and save the space on the screen. We're truncating so we don't see everything and make a big mess. Okay, so we can reach inside of the data frame and see its member, what they call member objects of the data frame class. So that's pretty useful. Of course, you could go ahead and access specific values. I showed you could access the two-dimensional array. Let's prove that you can actually look at a specific value. df values, which was that two-dimensional array with all the values. Now the first sample 0. The third feature, which is x, y, let's see, x, y, faces porosity. I believe that's porosity. And we go ahead and we run that, and you'll see porosity value for sample number 0 is that. And so we could go back and take a look, and you'll see that that's the porosity value. So you can retrieve any one of the values if you wanted to at any time using this member. So I've just proved that you can reach down inside of the data frame. You can grab any of the values. You could grab any of the names of the features. You can go ahead and work with those. At some point, you may actually want to switch and work with ND arrays from NumPy. And so you can go ahead and do that. What you'll do is you'll say df as an array, df, and there's a built-in function to NumPy. And this is pretty cool. How do I prove to you that it is an ND array? Well, I can go ahead and print out a string, which is the type of the object I made. That'll prove it. And we know that ND arrays, as I'll show in my next lecture, has a built-in member that is actually the shape which is stored, and you can access that and see how many rows, how many columns. And so let's go ahead and take a look at that. Okay, so we just made a NumPy ND array. We proved it. We just converted our data frame to a ND array, and the shape of it was 198 by 9 features that we're working with. Okay, I just want to show you that this is a deep copy. Now what we'll go ahead and do is we'll change that to 2 because we already got rid of the first sample. The first sample isn't there. And let's go ahead and run this. If you look really carefully, sample number 2, 0, 1, feature number 1, index 1, it's not equal to 10,000. And so we can see right here that this, in fact, is a deep copy. There's a bunch of Python built-in functions that you can commonly use. Things like list, len, length, and so forth. And so some of these Python built-in functions have actually been configured with a data frame as an argument. So what we can do, and I find this super convenient, the data frame has length df samples. So that's a nice thing to do. Use len. And if you look at the code I've already shown, I've done this before. Len df will just return the number of samples, the length of data frame. If you do the list command, it'll give you a list of all the features. Remember that columns, which was the member object that included the list of all the features? It'll access that and return that. So let's go ahead and run this, and we can see, in fact, it's telling us the number of samples, and it's telling us all of the features, including our truncated porosity, our categorical feature that we feature engineered before, right? Okay, so this is pretty useful. I do that all the time in my coding. If I want to do a calculation where I'm doing some type of a fraction or ratio or proportion, I'll often do length here, so I'll know how many samples, and then I can calculate the proportion of samples that exceed a threshold or something like that. How do we directly edit data frames? Like, I mean read and write to data frames. And if you want to do that, the .at member function is the control freak version for the data frames. It allows you to basically be able to take any individual one sample, one feature at a time, one entry at a time, and just read it and write to it. So it gives you full freedom to just interact with and work with your data frame, one sample at a time. And so if you look at it right here, the value of the first porosity sample was, and so df.at first sample, the zero index, porosity. And then what I'll do is I'll take that same value and assign over it using the at command again. This access that one value, and I'm saying make it equal to 0.2. And if I run this code, and now I'm just taking a look at it again. And just kind of mix things up, I'm using the LOC command to take a look and read it. We've already talked about that. And if we look at it, the value of the first porosity sample was 0.1184. We've looked at it before. We've seen that. The value of the porosity for sample 0 is now 0.2. So we reassigned it. So we read it, that one value, and we wrote over it. So the .at member function is great for being able to be a control freak and read and edit individual samples in your data frame. So we can do that. We have access to it like that. You'll find in many of your workflows, you need to be able to, in fact, save out things. Your workflow might be very complicated. It might take a lot of time. You might be generating intermediate files. You don't want to just run the whole thing in one shot. You might want to share a product with another platform. You might have moved to something else. You know, so clearly you need to be able to save out. So data frames have tons of methodologies by which we can save. If you want to save back to a comma delimited file, you have a built-in member function for data frames called tocsv. Now you'll notice that's completely analogous to what we did before, where we were reading the CSV file. Now we're going to save back out to the CSV file with all of our edits, all of our feature engineering, whatever we may have done here. The methodology we use is just to say df, whichever data frame we want to save out, to CSV, and the name. Now you could put a full address here. What I like to do for code readability is, of course, I like to use the explicit setting of the current directory. That's because in many of my complicated workflows, I'll move between directories because I have a bunch of different files, intermediate files, I have more kind of final files, I have diagnostic files, and I'll have different directories so that I can organize my project as I go along. Okay, so that's saving out the file. Now we can go ahead and run that command right there, and we've saved out the file. Now, what I'll do over here is I'll just go to that directory. I'm going to open it in with regular just Notepad, and that's the file right there. So you look really carefully, you're going to see we have the truncated porosity, the perm pore, porosity 100. All of our new features have been added into the data set. We've actually removed the first index, which is the second sample. So we've actually managed to go ahead and create a brand new data set with all of our stuff saved into our modifications. Okay, so that's saving a data frame to a file. Very, very useful. I sincerely hope that was helpful. I do believe that all of the different methods and member functions and blocks of code that I've shared with you should be sufficient to be able to build 90% of workflows in data analytics, geostatistics, and machine learning, working with tabular data. Of course, if you need to learn more, you will. You'll continue on that journey. Go ahead and use Pandas docs, which are great. Go ahead and use Stack Overflow. Go ahead and Google search questions. You can easily build up your capabilities beyond what I've shown here. Once again, I'm Michael Perch. I'm an associate professor at the University of Texas at Austin. I share all of my content online to support my students with evergreen content that outlasts the course, working professionals, and anyone interested to learn. I like the idea of providing accessible education. Go ahead and check out these links. You can see my Twitter account where I share daily resources on data analytics, geostats, and machine learning. My GitHub account where I share a lot of example workflows, well documented, and Google Scholar, of course, my book, my YouTube channel, and so forth. All right, stay safe.